So there's another practical consequence of our first fundamental theorem of calculus. And it goes like this. It's called the mean value theorem for integrals. It says if f of x is a continuous function on a closed interval from a to b, then there exists a number c in the closed interval from a to b such that the definite integral from a to b of f of x dx will be equal to f of c times b minus a. And we think, well, how is this like our intermediate value or mean value theorem that we developed for derivatives? Well, a good way of thinking about this is that the region that we always have underneath the curve, f of x, that region is our definite integral, right? So our region R, if we want to think about this like it being an area, right? Our region R right here, now that could be found by using our definite integral. But what about the rest of this? Well, if we go back to our ways of estimating area under a curve, one way that we estimated an area under a curve was to use rectangles. And let's say we happen to just choose one big rectangle instead of lots of little rectangles and said, well, here's our estimate starting at A, right? Our height is f of A, and our width is b minus a for this rectangle. Okay, so this is our width right here. This is our height. Well, clearly this is an underestimate. We could also find a higher rectangle right here, a value that rectangle that would be bigger, this time at the maximum of the function's value on the interval from a to b, and use that as our estimate. How good an estimate is that? Well, obviously it's an overestimate of our actual area on the interval from a to b. Still, it is an estimate, and its width would be b minus a, and it would be f of b in this particular case, in this example right here. But how do we actually get the estimate? Well, what this rule is telling us, get rid of these guys, is that somewhere on the interval from a to b, there's got to be at least one number c, some sweet spot on this interval that we can identify such that if we find the value of f of x at that point c and use that as the height of our rectangle, then the height of the rectangle at that point c times b minus a would be equal to the actual region R. In essence, we're equating these two things. Well, that's actually a very useful little tool for us right here, and we'll see that in a bit, but we might be able to use this function to find this value c if we tried. Let's check something out here. Let's try this out. Let's say we're asked to find the value of c guaranteed by this mean value theorem of f of x equals the square root of x on the interval from 1 to 4. All right, so what are we guaranteed to find? Well, on the interval from 1 to 4, we've got a is equal to, I want to get my pen back here, we've got a is equal to 1, we got b is equal to 4, but we need to find some value of c that satisfies this particular requirement right here. So we are going to take our antiderivative, or sorry, definite integral on the integral from 1 to 4. So let's see, let's go from 1 to 4 of x to the 1/2 dx, which means that we're going to be evaluating 2/3. Try that again here. We're going to be evaluating 2/3 of x to the 3/2 on the interval from 1 to 4. So doing a little bit of math right here to find our value, 2/3 of 4 to the 3/2 power minus 2/3 times 1 to the 3/2 power means that we're going to be taking 2/3 times the square root of 4 cubed, that's 8. 8 minus, well, this is just 2/3. All right, so a little bit of work right here gives us 16/3 minus 2/3, which is 14/3. All right, so what about our interval? Well, we need to be able to find something that's going to tell us that our value of our definite integral, 14/3, is going to be equal to the square root of some value c times, we have our value here, times b minus a. So that will be square root of c times 3. All right, so well, square root of 3c times 3, we're going to do a little bit of solving right. So when we multiply, of course, we're going to get 14/9 is equal to our square root of c. And of course, if we square both sides of this equation, we're going to get c is equal to 14 squared over 9 squared. So the number c equals 296 over 81. This would be the value at which we would take the function times 4 minus 1 and get the area under the curve.